Hello everyone, welcome to another video of thermodynamics. In this video, we will discuss how to use the first law of thermodynamics for an open system. For this, we're going to consider another problem. So the problem number 2 here, air enters an adiabatic compressor at 100 kPa and 300 Kelvin at a rate of 0.5 kilograms and leaves at 600 kPa and 450 Kelvin. Neglecting kinetic and potential energy changes, determine the volume flow rate of air at the compressor inlet and the power input to the compressor. So in this problem, we'll talk about a process in a compressor. So compressors compress air, compressor compresses air, and here inlet condition and exit conditions are given, and the mass flow rate is given, and we are asked to consider that compressor is adiabatic and also to neglect the kinetic and potential changes. Let's see how we're gonna do this problem. Okay, first thing always is to draw a schematic. So for compressors, the schematic diagram is usually drawn like this. So this is the inlet to the compressor, state 1, and the exit to the compressor, state 2. So we have inlet conditions P1 was given, let's see, let's remind that again, 100 kPa and 300 Kelvin, and exit condition 600 kPa and 450 Kelvin. So you're gonna see that P1 100 kPa, T1 300 Kelvin, and P2 is 600 kPa, and T2 is 450 Kelvin, right? 400 kilo, yes. And then your mass flow rate is 0.5 kilograms per second. So mass flow rate is m dot throughout this is 0.5 kilograms per second. So we are asked to find the volume flow rate at the inlet to the turbine. To find the volume flow rate, we have the mass flow rate. So if you find the specific volume at that state, you'll be able to find the volume flow rate. So or we can find the density, then we can also find the volume flow rate. So if you have the definition of density, is mass per unit volume. So mass divided by volume is the density. So we have we can take its mass flow rate divided by volume flow rate as well. So this is volume flow rate is equal to mass flow rate divided by density. So that's my equation 1. And assuming air is an ideal gas, right? Air is an ideal gas. You can consider air as an ideal gas. We can write P V equals mRT. So P is pressure, V is volume, M is mass, R is gas constant, T is temperature. And I can write it like M divided by VRT. P equals M divided by VRT. So M divided by V again is rho density, right? This is rho. rho RT. This is P. Okay, P rho RT. So rho is equal to P divided by RT. So now we can find rho. This is my equation 2. From equation 2 to 1, substituting, V dot is equal to M dot divided by P divided by RT, right? And you can actually take RT into the numerator, M dot RT divided by P. That's your V dot, right? M dot RT divided by P. When M dot is given 0.5, so we need to find V dot 1, that's at inlet, M dot 1 RT1 divided by P1. I didn't put R1 because R is constant, right? So for air, if you look at the tables, I'm going to go to tables to look at properties. Here you go, tables. So you can see properties of air at various temperatures. This has at 300K, so we're going to take 300K values. For air, R is 0.287. So I'm going to use that value. This is that value, 0.287, right? I'm going to use M dot is 0.5. This is times 0.287 kilojoules per kilogram per Kelvin, 300 and divided by 100, right? So if you multiply that, we use that for our calculation. Let's see, yeah, 0.5 times 0.287 times 300 divided by 100. You get 0.4304. So the volume flow rate at 1 is 0.4305 cubic meters per second. Cubic meters per second. So that's the volume flow rate of air at the compressor inlet at state 1. State 1 is a compressor inlet. So we solve the first part of that problem. And at the second part, the power input to the compressor. So power equation is related to the first law of thermodynamics. So we're going to apply, assuming that we have assumptions, assuming steady state. We need to have assumption for steady state. Assuming steady state, apply first law for process 1 to 2, right? Process 1 to 2. We're going to apply that Q dot minus W dot equals plus M dot 1 H1 plus V1 squared over 2 plus GC1 minus M dot 2 exit H2 plus V2 squared over 2 plus GC2 equals 0 because it's steady state. Now it says adiabatic turbine. This let's go to 0. And neglecting kinetic energy changes, these two cancels. Neglecting potential changes, these two cancel to each other. And then we have W dot plus M dot 1 H1 minus M dot 2 H2 equal 0. Okay. Now From mass conservation, m.1 minus m.2 equals 0 because it's steady state. Now we have that will give m.1 equals m.2 equals m dot, which is actually 0.5 kilograms per second, right? Now I'm going to substitute that into this equation. Let's say equation 3, and this is equation 4. From 4 to 3, by substituting W dot equals, I'm going to move that to the other side of the, to the right hand side of the equation, to this side, to the right hand side of the equation, and that will give me m dot h1 minus h2, right? M dot times h1 minus h2. For ideal gases, we can either use tables to find h1 and h2, or we can use constant specific heat analysis. So by using constant specific heat analysis, what you do is you can think that Cp is constant, and then constant specific heat analysis, let me write that. From assuming specific heat are constants, specific heats are constant, W dot equals m dot Cp T1 minus T2. M dot is 0.5 Cp. Now you can go to the table again. Cp is 1.005, that constant value. Cp is this, and you're going to go back to the workout. So it's 1.005. T1 is 300 minus 450, so that's 150. You get 0.5 times 1.005 times 150. It's 75.37. So we have, this is negative 75.38 kilowatts, right? Why do we have negative number? Now this term in this equation, this term W dot is work output, right? Work output. Now, in this case, we get work output is negative. That means this is work input. Therefore, work input to the turbine is 75.38 kilowatts. This negative work input output is, it's a work input, right? Okay. And if someone wants to calculate using variable specific heat, variable that means we actually Cp changes with temperature. So that changes can be taken into account by looking into the tables and find H1 and H2 from the table. So if you have that value, you have to go table is 16, m dot is 0.5, H1, let's look up H1. Let me see. Let me do like this. So from table A16, remember H1 at 300K. If you know the temperature, you can find the value. So you go to A16, 11, A12, 13, 14. Yeah, this is properties of uh, A17 actually. Properties of ideal gas, properties of A17. So at 300, you have H is 300.19. At 450, it's 451.80. So you know the temperature, you know the enthalpy. So 300.19. This is H1, 300.19 kilojoules per kilogram, and H2 at 450 K. H2 is 450. Let's see, 451.80. 451.80 kilojoules per kilogram, right? Now you're gonna do W dot is equal to M dot is 0.5 and H1 is 300.19 minus 451.80. And you solve this 0.1 times 300.19 minus 450.8, let negative 75.30 to get negative 75.3. You can take 31 kilowatt, right? W dot. So again, you get the work output, work input to the turbine is equal to 75.31 kilowatt. Okay, so all these answers are correct. There's a very minor difference between the constant specific heat analysis and variable specific heat analysis. You can follow either. If nothing is given in the problem, but if problem specifies you to follow constant specific heat analysis, so I have to change the table number is 17. Okay, you can do that. Table number is 17 includes all the values, so you can find that. Well, thank you very much for watching this video, and please join me with another video later.